this is now chapter 5.3. First, I want to say there's a lot of slides, more than normal in this section. And a lot of it, though, is not lecture, it's problems. I just put up a lot of problems. I feel that sometimes some students need more examples than others, specifically with answers to help you understand. So this has majority of slides are problems with answers, not necessarily the lecture. So if you are trying to print this up, do not panic when you see that. Okay, so let's get started. So in the last lesson, we introduced the formulas and charges for common mono, which means one atomic, and polyatomic ions. In this section, we're going to look at ionic bonds and compounds and how to write the names and formulas for these compounds. Okay, so ions. Ionic opposite charges attract each other. When positive and negative ions come near each other, they stick together tightly. The force of attraction between the opposite charged ions is called an ionic bond. So it's not technically a bond in itself as that we think like maybe like a dash to it, but it's electrostatic attraction. It's the opposite of charges that attract and hold each other together. So a compound composed of oppositely charged ions is an ionic compound. Many ionic compounds contain metal cations and non-metal anions. So if we look here, this is a slide from another one of my courses. Ionic bonds occur when valence electrons of a metal atom are transferred to the atom of a non-metal. So this is where the cations and anions come from. So if you see here in this little GIF I found, that sodium, once it loses its electron, is positively charged. Chlorine, once it takes that electron, is negatively charged, and this is how sodium chloride comes together. These two ions of opposite charge are attracted to each other and are tightly bound because of those opposite charges. Covalent bonds, we're going to talk about that later, so don't worry about that yet. We're only focusing on ionic bonds right now, but here are some depictions. You can see they're transferring exactly what you see here is what's happening. Transfer of electrons to the non-metal. So the metals give away the electrons, non-metals take them. And you can see that now what will happen is that these will come together because of those opposite of charges. So this is also very similar to sodium chloride. Sodium being the purple, chloride being the green. And ionic compounds contain many cations and anions that are joined together through ionic bonds. So what will happen is if you have one type of, let me go back. To understand how these ions fit together, look at the structure of the compound composed of sodium cations and chloride anions. And a single sodium ion and a single chloride ion will come together. But what if you have more of them? Then they end up doing this alternating pattern of positive and negatively charged ions, eventually forming this 3D array. They call this a ionic lattice structure because it's linked because of the charges, and they become bigger and bigger by having more of the opposite, the cations and anions come together. And they will lay this way because of the charges. They will stay away from same charges, but they will be attracted to the opposite charges. Okay, so chemical formulas. Okay, so now let's take a look at chemical formulas. To represent the composition of compounds like this one, we use a chemical formula that indicates the type and the amount of each element present. We represent ionic compounds using a specific type of chemical formula called empirical formula. An empirical formula gives the smallest whole number ratio of atoms in a compound. So it'll always be whole numbers. It will never be a fraction. An empirical formula gives the smallest whole number ratio of atoms in a compound. Sorry, I just read that. Subscripts written after each atom indicate the number of that atom present. If no subscript is written, as seen here, for instance, in sodium chloride, it is understood to be 1. So in this instant, the formula is written simply as sodium chloride, so by default, when you see that, this means 1 sodium and 1 chloride. The empirical formula gives the smallest whole number of ions necessary to form a compound. The number of ions is called the formula unit. For example, the empirical formula for sodium chloride is sodium chloride. That is the smallest number of ions necessary to form a compound. A formula unit of sodium chloride contains 1 sodium ion and 1 chloride ion. When writing empirical formulas for ionic compounds, we write the symbol or formula for the cation first, followed by the anion. So even though when we're dealing with ionic compounds, they're more like this. All we need is to show one that makes up the whole unit. And for this case, sodium chloride makes up the whole unit. What about when you have more than one? So here is an ionic compound with different charges. So we have potassium, which is a +1 charge, and we have sulfur, which is a 2- charge. So some ionic compounds contain cations and anions with different charges. For example, consider the solid composed of potassium and sulfide ions. The potassium cation has a charge of +1, while the sulfide anion has a charge of 2 negative. To form a neutral solid, the positive charges must equal the negative charges. In order to balance the charges, the solid must contain 2 potassium ions for every 1 sulfide ion. This makes the total of the positive charges and the negative charges equal an overall of 0. So you need two potassiums, which equal +2, to cancel out the -2 of the 1 sulfide ion. So when writing empirical formulas for ionic compounds, we write the symbol or formula for the cation followed by the anion. We write this as K subscript 2 and an S. But we'd say we would call this potassium sulfide. So is a formula unit of potassium sulfide contains 2 potassium ions and 1 sulfide ions. This is now a neutral compound. We do not include the charges of the ions when writing them out. These are things that you would just have to know about potassium. If you had to figure it out, you would know that potassium's a group 1, has a +1 charge, and you're going to need 2 of those to cancel sulfide, which has a -2 charge, and that's things that you are going to have to memorize and learn. We do not write out the negative and positive charges. So compounds with polyatomic ions. We can also predict the formulas for ionic solids containing polyatomic ions. Look at calcium. Calcium is a group 2, so it loses 2 electrons. And nitrate is a polyatomic ion that has a -1 charge. So in order to cancel out the 2+ charge, we're going to need 2 nitrate polyatomic ions in order to balance this out. So it'd be 2+, and then we have 2-, canceling out equals 0. So we write the formula as, so total charge is 0. But how do we write this out? Well, how you write this out is you take the calcium and you put inside parentheses the polyatomic ion and a 2 subscript below. This means that you have 2 nitrate ions for this. So what does this mean? This means you have 2 nitrogens and 6 oxygens, which is what you have here, 2 nitrogens and 6 oxygens. So you multiply this and you multiply this. And this will equal a 0 charge for the overall compound. And we write it out again, Ca parentheses NO3. We keep the polyatomic ion intact always. This is one whole unit. And then the 2 on the bottom, which is right here, indicates that we have 2 of them. And you always write that in superscript outside the parentheses. So let's take a look at another one. Here we have aluminum, which has a 3+ charge, and we have sulfate. So we have, so we need to write a formula for this. So we have 3 sulfates, which equals a -6 charge. Well, in order to have, we need to balance this to equal 0. So if we have a -6, we need 2 aluminum cations in order to cancel them out. So we need to balance this out. So +6 and -6 equals 0. So how do we write this out? Well, this is how you write it out. We have a 2 charge. We have 2 aluminums. So we write aluminum and we write a 2. And then in parentheses, we write the sulfate, and we have to account for 3 of them. So this is where the 3. So let's see, we have 3 sulfurs. We have 3 sulfurs. Here we have 12 oxygens, 4, 8, 12 oxygens. So this accounts for everything. This is now a neutral compound. Okay, so these are, the next few slides are mine from another course. This is a checklist of how to write them out. So this basically is going through telling you how to write this out, what not to do. And I'm now going to show you an easier way to, oh, look at, I forgot a parentheses here. There should be a parentheses. I'm now going to show you an easier way than doing it like this. I don't like this. Your book's showing you that way. Yes, that's the correct way. but I also know a shortcut. Crisscross. Write formulas for ionic compounds that form from aluminum and oxygen, magnesium and oxygen. So the key thing is you have to know the oxidation states, the charge states. Have to know them, and they have to be correct. So for aluminum, for instance, we know that it has a 3+ charge and oxygen has a 2-. So now, remember, these still have to equal 0. Crisscross them. So take that 2 and crisscross it and put it as a subscript for aluminum, and take that 3 and crisscross it and put that for oxygen. Now, let's see. We have a 3+ charge and we have 2 of them. So that's 6. So 3 plus 3 is 6. And then we have 3 here, and we have a 2. So 2, 4, 6. 6 plus, 6 minus, they equal 0. Magnesium, we have a 2 plus, and we have an oxygen with 2. Crisscross them. Now, this is hard to explain, but actually it's not. It might just confuse some of you. This is how we crisscross them out. Your book wants you to do it this way. And you should know how to do this, because if you crisscross it and it doesn't cancel out, something's wrong. So by knowing the charges and counting how many you have, as long as it equals 0, the overall, it's fine. Now there's one more thing you need to know, and your book didn't tell you. So here's magnesium as an ion, and we have oxygen as an ion. We crisscross them down. Now the whole thing says to have the smallest ratio of whole numbers. Now the problem is it didn't tell you that in certain cases you can't leave it like this. So writing magnesium 2 and oxygen 2 like this is wrong. You did exactly what it's supposed to do, but there's one more step, which I have here in number 3. If possible, reduce the subscripts to give a ratio with the smallest whole number. And I forgot an I in everything. Everything must be able to be reduced down, or you can't do it. So what does that mean? Well, I can't reduce this down because if I reduce, I get fractions. But I can reduce this down by dividing both by 2. And these are these fun little things about chemistry you're just supposed to know, and you're supposed to just do. With still knowing that once you remove these 2, they still exist because these charges still exist. We've just reduced it down. So I'm going to show you an example. Here is that magnesium, but now we need to follow rule 3. We need to divide it down. So when we divide it down, we end up with, in bold here I have it, magnesium oxide, which is magnesium oxide. This is still magnesium oxide. The name hasn't changed. And you still have a 2 negative charge and a 2 plus charge. However, we just removed the 2's there because we can reduce them down. These are the fun things about chemistry. You're supposed to just know how to do, and you're supposed to just know how to do those charges. You're not going to escape it. It will come up. Okay, so let's do some chemical formulas. Now we're going to get to a lot of examples, which is why a lot of this lecture is so long. It just gave you a lot of examples. So let's write the chemical formulas for these. So crisscross them. All right, so the first one we did, we crisscrossed them, and now we also reduced it because we had to reduce it down. If you left the 2's, that would have been wrong. Zinc and chloride, crisscross them. We have zinc, and the 2 goes on the chloride because you have a negative 1 charge. You're going to need 2 of them to account for the 2 plus charge. And iron 3 oxide, crisscross them. We now have iron 3 oxide. How would I know that? Well, if you're given just this and they're asked for this, you have iron, crisscross it, iron 3 oxide. And that's going to tell you how to say that. Okay, so naming ionic compounds. So those slides were from mine. This is from your book. How do you say this? Sodium chloride. When there's ions, you just say it. Doesn't matter what the subscripts are. Magnesium chloride. Magnesium sulfate. This is another one. I put it in that big box. You have a 2 and a 2. You would have to reduce that down. That's why in magnesium sulfate, you don't see the 2 charge on either of those because it's been reduced down. Naming cation. Okay, so in this case, do the crisscross, even though it's not asking to do that. So you have copper, and you don't have anything here. So this must be copper 1 chloride. You have copper, you have a 2 here. So this must be copper 2 chloride. Look at the crisscross still. All right, so this is your book. This is not mine. Mine are crisscrossing, but you can still do it because you have it right here. So iron 2 nitrite. Iron 2 nitrite. Here, ammonium. Ammonium is the only positive one out of the polyatomic ions. Sulfide. So once you know what the plus charge is for this and the negative, the two negative here, you crisscross them. So see, the -2 would crisscross, put in parentheses, and this is how you would write it out. All right, these are my slides again. We can determine the charge of the metal from the chemical formula. The sum of all the charges must be 0. The charge of an iron in iron 3 chloride must be a 3+ for the compound to be charge neutral with 3 chloride ions. The name of iron 3 chloride is the name of the cation, ion, followed by a specific charge in the parentheses. So this is just review. Followed by the base name, which is chlor, and ending with the "ide." The full name is iron 3 chloride. This is just a review because there's a lot of naming and a lot of different rules. All right, so name the ionic compound FeCl2. Crisscross it. We're dealing with iron 2, and we have chloride. And even though we have 2 chlorides, that doesn't count here. We're not interested in that. This is the naming. So this is iron 2, no space in between, parentheses, chloride. Again, I'm just giving you this slide that I've given you prior to help you out. All right, name the following ionic compound containing a variable charge metal. So we have SnO2. First of all, what is Sn? So if we look here, it is tin. So let's just jump ahead. I'll just cheat. All right, so we have tin. We have oxygen. This is a transition metal. We need to know what the state is. So this one is a hard one. Why is it hard? Because if you looked at the oxidation states for tin, it's either 2 or 4. There's not a +1 there. So something's going on here, right? Because if it's a 2, then both of those would reduce down. But it didn't. There's still a 2 there. So this is showing you how to solve for something if you don't have enough information, which students hate to try to solve for the oxidation state, but sometimes you have to do it. So what do I mean by that? Well, we know that oxygen has a -2 charge on it, right? And we have 2 of them. So we're going to solve for the tin oxidation state. So we make it an X. And we plug in what we know. We have 2 oxygens with a -2 charge. This means X minus 4. We solve for X, we have a +4. So this means that tin has an oxidation state of +4, and it was reduced down because we were able to reduce it, leaving a 4. So remember, we crisscross these. So if this has a +4 and this has a 2, this 2 would come down, a 4 would come down, and we would reduce them now, leaving the 2. Hopefully that makes sense. If not, you guys can contact me. Or just write it out yourself. Write this out and figure it out, and you'll see. Make this a +4 and a -2 and crisscross them, and then you'll see what I'm talking about. All right, so how do you say this? Well, it's tin, no space, 4, oxide, tin 4 oxide. Okay, so why is calcium oxide not calcium 2 oxide? That's very simple. Calcium only loses 2 electrons. It's in group 2. It will always only lose 2 electrons. It doesn't have different oxidation states like the transition metals. So you don't need to write the Roman numerals. Okay, so naming ionic compounds. These are a lot of my slides from other, just to give you guys more examples. So example, we name potassium nitrate. We have potassium and we have nitrate. And this will crisscross and it crosses out. So it's just one whole word because that's a negative, that's a positive. But we name iron 2 oxide according to its cation charge. So we have to crisscross this. So this has a negative charge. So if we crisscross it out, and then the 2, which has a +2 charge, crosses over. So there's a +2 here. Here is a negative, so that negatives here is a default of 1, and then the 2 comes over. We need 2 hydroxides in order to cancel the +2 charge on the iron. So this is iron 2 hydroxide. And we have ammonium nitrate. Both of these are a plus or a negative. We cross them over. It's a 1 and a 1. So we have ammonium nitrate. Okay, write the formula for a compound composed of magnesium and chloride ions. So they want you to do it their way. I'm going to tell you to crisscross them with the charges. And you see it's magnesium MgCl2. Write the formula for the compound composed of lithium and sulfate ions. Again, all of these can be done with crisscrossing. Why? Because you have this, and you have this. This crisscrosses over, it would be a 1. This crisscrosses over, and there's a 2. Write the formula for the compound composed of calcium and bromine and iron 3 and sulfide. and iron 2 and phosphate. Crisscross these. You can crisscross these very easily. You can see it here. This one's done. And this one you have to pull out. So this is iron 2, so it'd be a +2. Phosphate has a -3 charge. And you can see they were crisscrossed over. Naming ionic compounds. I'm just going to go through these. I've given you a lot of examples to help you get more familiar with this stuff, because I think sometimes more examples make life a lot easier and makes you feel more confident that you're actually doing what needs to be done. So on the left side, they want you to write formulas. On the right, they want you to write the name. So I'm giving you all of this. There's a lot of slides here, and it's simply just to help you get comfortable in knowing how to write these out, especially with the polyatomic ions. And you really won't get better at them unless you do them. Here's another one I want to point out. So zinc has a 2+ charge. This has a 2- charge. It's reduced down to zinc sulfide with no number showing. Copper 2, here's another one. Copper 2 has a +2 charge, -2 charge. They've been reduced out. Another one, and this is the one that throws people off, aluminum nitride. There's no numbers here, okay? Aluminum has a +3 charge. Nitride has a 3- charge. They crisscross down, you reduce them down. Okay, so what is the formula for magnesium phosphate? I'm just going to jump ahead to give you guys the answers. These are ones I feel that you can go over and look to make sure that you are understanding it, and you can go back and see what were wrong if you didn't do them right. But this is why you have a lot of slides. It's because I gave you a lot of problems to help you to get comfortable with this. In summary, ionic bonds occur between oppositely charged ions. In ionic compounds, the total charge has to equal 0. We name the cation, then the anion, and you should be able to jump very easily between the formula and the